So I like this section. This is a pretty fun section because this is where we get to start to do some somewhat interesting application questions. We'll get to several of those. You got some of those in your extra practice as well. And so this is it, guys. This is it. This is our final topic for the semester. Like I said, we'll take the rest of this week to try to kind of digest all this and learn how to apply everything. But it really is just one topic alone. And I'll try to present it as such. So if at any point, I really honestly say this, if at any point it seems like I've gone off course, like if the principle that I'm about to talk about seems to not apply somehow, and you're like, whoa, I thought it was always this, and now you're saying it's that, please ask, right? Because there's going to be a good reason for whatever it is we're doing. But if something seems to be, not equating to how you think it should be, please ask, okay? So here it is. This is it, really just in a nutshell. The net change theorem is right here. The definite integral of a rate of change gives the net amount of change. It's really easy to not see the important change in wording there. I underlined it. I'll circle it. So if you do the definite integral of a rate of change, you will get the net amount of change. So give me some examples of rate units. Meters per second.
Donuts per hour.
Gallons per hour. How about ice cream cones per minute? Or like our friend yesterday, donuts per hour. Donuts per second, maybe would be a better measurement, yeah. Those are all examples of rate units. What about units for amount? Donuts. Say again? Mats? Yes, we have a significant number of those. Yeah, there's no, like with an amount, there's no per whatever, right? There's no per time associated with an amount. So the definite integral of it, a rate of change, gives you the net amount of change. I thought we'd look at a couple of these, and I'm going to actually have an additional one on the board for you. So velocity. We'll consider the units here in a second. The definite integral from A to B of V of t gives you the net change of position. Why would that be? Well, let's think about the units. What kind of units go with velocity? Meters per second, yeah, distance over time, sure. So I'm going to say meters per second. What kind of units would go with the dt? Seconds, right? Because dt just means like a little tiny change in time. So I'd say times seconds. And what happens with the seconds in that case? Cancel out, leaving you simply with meters. So we're basically doing the integral from a to b of meters. And what is a definite integral? Like by definition, like what is it?
Infinite sums.
It's an infinite sum of little skinny things, right? And so if we're going to just add up a bunch of meters, this would probably end up giving you meters. Okay, we'll come back to that one a little bit later. But for now, let's move on to the leaky tank. We've all seen this. So if L of t stands for the rate that the tank is leaking, what might be some units that you could go with L of t?
Drips per second.
Drips per second. I'm going to go with that. Everybody wants to say gallons. I'm going with drips per second. So I'm assuming drip is like a volume unit, right? Like the size of a drip. Sure. Okay, so then the dt, like before, would be measured in seconds. And so the seconds would cancel out. So we'd end up with the definite integral from a to b of drip size. And so if you added all those up, you'd have a large number of drips perhaps, and you'd have an amount. And so the definite integral from a to b of L of t would give you the net change in the tank, or net change of the water in the tank. If it's water, I guess we don't know if it's water or gasoline or whatever. Okay, so then the general principle is the definite integral from a to b of a rate gives you the net amount of change. So I thought we could look at this, like this is like a somewhat of an application perspective. I want to also look at this just in terms of like a generic function here in just a second, but first your question.
I have a question. On the leaky tank one, if you said like the derivative is like the net change of the drips, is that wrong?
This a little, I mean, because you use drips for a unit,
Yeah.
that's a little shaky, right? I think gallons would probably be a little bit better because is it the number of drips or the volume of the drips?
Yeah.
I don't know.
Because I just like when
Yeah.
the seconds cancel out, you're just left with the
Yeah, number of drips. Or is it number of drips or is it volume of the drips?
Volume of drips.
I don't know.
Okay.
He said drips. Ask him. I would prefer gallons from that perspective. All right, so I want to show you is we're going to change the wording. We're going to say, we're going to erase that first phrase and we're going to say the amount, AMT, right? The amount of gas is, come on, there we go, is changing. So the amount of gas is changing at a rate of R of T, gallons per hour. So let's get rid of the old, let's just please forget that you saw anything about anything flowing out of anything. Just pretend like that's not there. I think that's very bad wording based on the way this question actually takes shape here. So the amount of gas is changing at a rate of R of T gallons per hour. The graph of R of T is shown off to the side there. The tank contained 1,150 gallons of gas at T equals 0. It gives us kind of one directive and then sort of an implied directive. Write an expression for the amount of gas in the tank at time T equals 3. And then it gives some areas between the t-axis and that graph off to the right. So it gives us a couple things there. Well, it's going to enable us to get kind of a nice numerical answer in the end. But I want you guys to focus on this right now. Write an expression for the amount of gas in the tank at time t equals 3. So in the other class, I was kind of thinking that I would do this with them. But as soon as we read this together, they just started writing and they thought they could do it. Do you guys think you have a shot of doing this? If you do, go ahead and give it a shot. I think that if you really do get this, you should be able to have it written down in like maybe 1 or 2 minutes. It shouldn't take you too long to just get the setup written down. And after a minute or two, if you don't get it, that's fine. We'll go over it together, but give it a shot.
Minus the initial amount.
So, but tell me exactly what's right. I don't think you want me to write that sentence. Give me some math stuff to write down.
So, negative 150 plus 100.
Oh, I see. Okay, so can you take it back one level? So can you write an expression? So I'm not saying that you're wrong. I think if this were a quiz or test, I think I'd word it to try to get you to do what I want you to do. Can you write an expression with an integral in it?
So the integral of A or B and A.
I think you'd be more specific than B and A.
0 and 3. So 3 and 0
So integral from 0 to 3
is equal to
of what?
R of T.
Okay, of R of T.
And then dt equals negative 150 plus 100 minus 75. That's equal to that minus.
Hey guys, hey, the chit chat, hold off. Paul has done some really interesting things here, but you kind of faded there. You said something
So
about,
that minus the amount initially, because that would be the final amount minus the initial amount.
so I have it written down exactly as you intend.
Pretty sure.
I just want to make sure. I'm not saying it's right or wrong. I just want to make sure I have it written down right.
Yeah.
Okay. Okay. What do you guys think?
Or that would be equal to,
Oh, sorry.
that would be equal to some value minus that amount. Or something. I'm trying to explain this.
Okay.
Yeah.
What do you guys think?
I don't think that the 1150 at the end should be.
So you think this needs to go away?
I think so.
Okay. Other thoughts? So he thinks there's something wrong. Do you guys, let's just establish this. Does Paul have some significant things right for sure? I agree. I think for sure there is no doubt that Paul has some significant things right, but I agree that he's got some things wrong. Okay? So let's do this. Let's go from left to right. Let's analyze this. This expression right here, I think is very, very good, right? This is a good start. This is exactly what we want. But we want to be super careful that we understand what that is. That's the definite integral of a rate. And the definite integral of a rate is?
And that change area under the curve.
It's associated with that, but in context of this, it's like the net change of the amount of gasoline. So this right here, I'll put it like this. This is the net change of gas, the net change of gasoline. This is where we want to be super duper careful that we understand what it is we're talking about. This is the net change The net change is not necessarily the amount that's there, right? So for example, if we did my whole goofy like growing thing, like if I was 5'9" now, I was 6'4" later on, if you came up to me and you said, whoa, wow, you know, your height's changed a lot, and I'm like, yeah, I grew 7 inches. You wouldn't look at me and be like, so you're 7 inches tall? That doesn't make any sense. I didn't tell you how tall I was. What did I tell you? How much my height changed. So the only way that the change in height or the change in gasoline is the same as the amount of gasoline is if you started with 0 height or 0 gasoline, right? So that integral that Paul told us right there is a very good integral. It's exactly right. But it's the net change. It's not necessarily the amount. Some other things that I think are very good. Paul equated that integral with this. Is he not correct? This does not belong. Matt was right about that. That does not belong. So if we got rid of this, isn't that equal to the net change? Now he went a little bit further than I was expecting, which is fine. He had like the negative 150 and the negative 75 and the positive 100. Do you guys understand why he made the numbers negative that he made negative? Because they're below the t-axis? Okay. So this right here, this is also the net change in the gasoline. And this is all well written and great and everything. But this has not quite answered the question, right? The question was, how much gas is in the tank? What else do we need to consider? And Paul sort of considered it.
You need to have the value of R3 minus 1150.
Why? You keep on wanting to subtract the 1150. I'm kind of curious why.
You said that the integral is equal to the amount. So,
The integral is equal to the net change of the amount.
okay, so then the net change would be the final minus the initial. Right?
Okay. So the initial would actually have to be added back over. Like the initial amount is not negative, right? The initial amount is positive.
No, from an unknown amount. Like you said it was. Like,
Can I write what it should be and then we can try to reconcile it what we're talking about? So I would say what we'd want to write would be this. 1,150 plus that integral equals those numbers plus 1150. Is that what you were trying to say? Okay, yeah. So I think we were just talking about two different sides of the same coin. I just wanted to try to clear that up. Does that make sense there? We're basically saying the initial amount plus the change in amount is equal to the final amount. So this whole thing over here would be the final amount. So if you take what you started with and you add the change, then you get the final amount. Say again, Paul? Oh, sorry, you're talking to Lauren. Okay, so what do you guys think? Does that work? Are you guys okay with like the final product here? Let's see here. The final product would be negative 125, so it'd be 1025. Is that right? 1,025. So what does that mean? If the tank started off with 1150 and it ended up with 1,025, what does that mean? That's how many gallons is left, right? But over the course of the 3 hours, what happened? Yeah, more gas left than came in. That make sense? What do you guys think? Do you have any questions on this one? I like this for a couple reasons. Number one, it's very conceptual, so you're not going to have to do a ton of really complicated arithmetic. As long as you can add some pretty basic numbers, you're okay. And you can show what you know without having to go through a lot of pain of adding things and subtracting things that are complicated. Any questions at all? Yes, ma'am.
So because the answer is positive, that's why it would be like more gas than...
No, so the answer, so this right here, this is the final amount.
Okay.
And so what I would say is based on the context of the question, I don't think there's any way we could have a negative amount.
Okay. Yeah.
Right? So I think, with we got gasoline in the tank, you either have 0 or positive.
Okay.
And so the fact that that number is positive simply means that we still have gas in the tank. What I'm saying is that we started this whole scenario with 1,150, and now we have something less than that.
Right.
And so that means more gasoline left the tank than came in. That make sense?
Good.
Okay. Anybody else? Okay, cool. All right, take a look here at Our next example, this is, again, the net change theorem. We're still talking about all the same stuff, but this is a different application of it. And this is using displacement and total distance. We have talked about displacement a little bit, but I don't know that we've talked about total distance all that much. So check this out. We'll look at this from a couple of different angles. The net change in location from the starting point to the ending point, that is your displacement. I always like to use the example of your guys' day, right? So if you woke up in your room this morning, in your bed, and then tonight you finish in the same place, hopefully, your displacement for the day, 0. That doesn't tell the whole story because you actually came here, right? So you actually did move. But as far as displacement is concerned, your displacement is 0 because you started and stopped in the same place. Total distance traveled, of course, is a little bit different. Total distance traveled takes into account the fact that you might have gone one direction and then gone back the other direction, and it considers those to all be positive distances, and it simply adds up all those positive segments of your trip and gives you a full picture of how far you traveled. So I'm going to look at this from two different perspectives. The first one is a graph. So if you guys would, maybe copy this graph down. We'll continue to talk about your day in graph form. So let's see here. The vertical axis is going to be v of t, and the horizontal axis is going to be time. And let's pretend like this is your day when you woke up. You know what? Let's do this from the perspective of your car. So your car sitting there, Barrett, you with us?
Yep.
Okay. Your car just sitting there in the garage or on the street or whatever. It's not moving. It starts the day moving with 0 velocity. So that's what that first data point is. It's not moving. Then you get in the car, you turn it on, you start going, right? So think about it like this. As you leave your house, isn't the distance from your house to your car increasing? And so because of that, I would say your velocity is positive. So you take off, you're heading to school, you get close to school, you start slowing down, and right about there, that's when you get to hopefully you're on time enough to get to a parking spot, and you park your car. It's not moving anymore, right? And then the day goes on, your car just sits there, doesn't move. And then right about here, it's the end of the day, and you're going to go home. So you go back to your car, and now you're heading home, and so the distance between your car and your house is now decreasing. So I'd say your velocity would be negative. And so it looks like this. Assuming the same traffic patterns be a similar looking loop there. But this time it would be below the t-axis because you're heading back home and your distance from your car to your house is now decreasing. Does this make sense? Okay, so then when you think about this integral expression off to the left, displacement is equal to the definite integral of velocity, we can think of this as simply accumulating the area. And so as I accumulate this area right here, I don't know, let's say that you live 10 miles from Valor. So let's say that this would be an area of 10, so the integral would spit out a 10 for that part. And then when you get to here, the area of that is also 10, but what kind of number would the integral spit out there? Negative 10, because it's below the x-axis. And so when it came time to figure out your displacement, you would say integral from, I don't know, let's say that this is 0 and this is 8 hours or something like that. So you'd go integral from 0 to 8 of v of t dt. Well, as you accumulate, you'd go plus 10, and then you'd go plus negative 10, and you'd end up with 0. So your displacement in that scenario would just be a big fat 0. But of course, we know that you actually moved. We know that you came here. And so we could maybe look at total distance traveled. Can you guys see that displacement and total distance traveled, the formulas are very similar, right? What's the only difference? So let's consider that. So if I were to then take this same graph, I'm going to try to line these up vertically as best I can. So if I was going to do a graph of absolute value of velocity, which happens to be speed, if I was going to do a graph of this, what does absolute value do to a graph? Yeah, it keeps it either on or above the x-axis, right? So this first loop would be totally unaffected. This little segment would be totally unaffected. But when you get to that last segment, instead of being below the x-axis, it would get reflected above. So it would look something like this. So then, as we think about accumulating area with this, if these two areas are still 10, when you think about total distance traveled, we'd go integral from 0 to 8 of absolute value of v of t. This time you would not get 0, you would get 20. So total distance traveled is always non-negative. It's either 0 or higher because of that absolute value concept. I want to show you one other way to think about at least displacement. Does this make sense so far? Hopefully the graphs help. Bless you. All right, let me show you one other way. Think about this. I'll just do this with velocity, or with displacement. This gets kind of messy with total distance. So think about it like this with displacement. Would it be fair to say that this expression is the exact same thing as the formula for displacement? Right? Velocity is position prime. Okay. So if I wanted to do the same kind of activity as I did up here, let's think about how this would work. Wouldn't this equal x of t? Oops. Evaluated from a to b. So then I could say integral from a to b of x prime equals x of b minus x of a. So then this is simply your displacement, right? It's where you finished minus where you started. That is your displacement right there. And displacement is equal to the definite integral of velocity. Take a minute, digest, think. Any questions? You get a chance to practice this here in just a second, but I want to give you all a chance to think it through. We good? All right. Let's do this. Here's your chance to practice. Together. Take a look at number 2. It's on the next page. ABC. I feel like, I think ABC, of those three, I think A and B are pretty cut and dried. And then C might require a little bit of thought. Please notice that for A and B, if you want to use Math 9, you're welcome to it. You don't have to. You could actually do this just on paper and pencil. But if you want to just use Math 9, I've got no problem with that here. Just a little practice with that would be good. So please take a look at A, B, and C for number 2. Give you a chance to do these, and then we'll check them over in a minute. A and B, pretty cut and dried as far as what you're supposed to do, but I do want to be super clear about what's expected of you. So for A, it wants displacement, so we'd write integral from 1 to 5 of v of t dt. Is it frozen? Sorry. Excuse me. There we go. And did you guys use Math 9 on this? So equals, okay, so 10.667. What kind of units would go on that? Not feet per second, actually. Feet. Because it's displacement. Displacement is associated with position, so it's that. So guys, I want to be ultra clear about this. I've said this before. It's worth saying again to save you heartache. If this were a quiz question and all you wrote was the thing that I'm putting in this blue box, you'd get no credit whatsoever. None. You'd go 0 for 2. Can I explain why? All you've done is you just thrown an answer out there, and yes, it happens to be the correct answer, and they won't always be this particular. I have no way of knowing what you did to get there. So let me explain how you get full credit. If you put everything in that blue box, can I explain why this is so significant? Writing this down is incredibly important, and here's why. You might look at that and say, well, gosh, like how hard was it for me to write that? Well, it shouldn't be very hard now, but I want you to think about yourself 3 weeks ago. If I had asked you question A 3 weeks ago, unless you had been doing some reading on your own or YouTubed some video, you would have had no idea what to do. You would have been like, you got me, I have no idea, right? But now, 3 weeks later, now that you've seen this, you write this down. The 3 weeks ago version of you would have never written that down. You would not even have known where to start. So the fact that you wrote down integral from 1 to 5 of v of t dt, That is very significant. Very significant. And then, yeah, you used Math 9 and whipped out the answer. No big deal. But writing down what you're actually doing is very important because you're communicating that, yes, as a matter of fact, I do know what I'm doing, and here's my proof for that. And then hopefully you get the right answer. Okay, and then the other one, integral from 1 to 5 of absolute value of v of t dt. And that's approximately, I thought I saw like 11 point something as I was walking around. 11.833. Okay, so 11.833, again measured in feet. Once again, if you want full credit, if you want any credit, you want to write down everything in that big blue box. You want to write down your setup with an integral, and then hopefully the right answer as well. Okay? Any questions? Beautiful. Does anybody need more time with C? I didn't want to cut you off short. We all good with C? Either like you have an answer or you're stuck?
Yep.
One of the two? Okay, fair enough. I want to give myself just a little bit more room. So let me do this. So we're just going to do C here. Guys, so a couple of notes. Please note this. I mentioned this to a couple folks as I was walking around. Notice it says write an integral expression for the position. It's not actually asking for an answer, is it? It just says write an integral expression. The other thing to pick out here is it says integral. So if you look at what you have written down for an answer for C and you don't see an integral symbol in there anywhere, categorically you're incorrect. Make sense? So you better, like, if you're hoping for credit, that thing better be in there somewhere in some form or fashion. Okay, so let's maybe shoot for a little bit more than that, though. Can I show you a couple different ways you might think about this? A physics student would maybe do this. Whoops. Physics student would maybe do this on the left. They would say, well, I know that the position when t is 9 is 4. They might think of that as like an initial position, right? So when t is 9, the position is 4. So they might say, well, in order for me to get the final position, I have to consider the fact that it started at 4. And then don't I have to consider the change in position? So it started at 4, and then maybe the position changed. So what I'm going to do is I'm going to add the change in position. And if I can go 4 plus the change, then that should be my final position, right? Do you see why that's logical? If I know where I'm at, and I know how much I moved, then I know where I am, like I know where I'm located. So instead of writing change, of course, maybe we would write this. Integral from t equals 9 to t equals 20 of v of t dt. And that would actually be a good expression for what it asks for. Number one, it's an integral. It's got an integral in there. And number two, I've considered both the initial position plus the change in position. That gives me my final position. We're going to think about this one other way, but I wanted to bring up one other thought with you guys, and it's this right here. What if that's what I wrote? Is that so terrible? I took away the 4, right? So is that just a terrible answer? It's actually a pretty good answer. It's not quite right.
4 still be in it though?
So I changed it. I want to get a little comparison here. I want you to understand why the 4 has to be there.
Okay.
So that right there is not a terrible start at all. Can anybody define what that is? Like if I said explain the meaning of that expression, what would you say? Change in position. Yeah, that's a change in position. And so the change in position is not necessarily the actual final position unless we started where? At 0. Yeah, so if we started at 0, then not only would that be the change, that would actually represent the position as well, but we started at 4, so we've got to put 4 plus to turn that into the actual final position. So the other way you might have thought about this, and maybe some of you did this, and if you did, that's great. You could have said, well, what if I did this? Integral from 9 to 20 of x prime of t dt. Did anybody do this? Okay. So the integral from 9 to 20 of x prime is velocity, right? Wouldn't this equal x of 20 minus x of 9? Using the same principle we have up here on the board, net change theorem. Wouldn't the integral undo the derivative? And then we know that x of 9 is 4. So we'd say, I'll try to squeeze this in here, integral from 9 to 20 of x prime equals x of 20 minus 4. Yeah? And then couldn't we just add the 4 over? And that would give us 4 plus the integral from 9 to 20 of x prime equals x of 20. So that's a little bit different because on the left we just have an expression, which is what was asked for, and on the right I've got a full equation. But do you see how the correct expression is within that equation? You know, equaling the thing that we were supposed to find. So I think like a physics student maybe would think about the way on the left, and maybe a math student would think about the way on the right. The math student would be like, hey, the net change theorem, the integral of a rate is going to be the net amount of change. Physics student's going to be like, hey, where did it start? How far did it move? Where is it? Right? Those are basically the fundamental questions maybe a physics student would ask. I don't know. And so that's all you had to do. If you were to take this and finish it and like use Math 9 and get an actual numerical answer for this, I'd be okay with that as long as you didn't make a mistake. But please note it only asked for an expression. It said write the integral expression, and so either whether I use the red or the blue one, I could just stop right there and I've answered the question. So don't go too far, if you can help it. Okay, I want to do one more. We're going to do 2 more examples here. I thought we'd do this one here. Math 9 continues to be useful. And this is more net change theorem stuff. So I thought we could look at this one real quick before we do our final example. Notice what you're asked to do here in this example. It says find f of 5. And let's think about what we're given. It says find f of 5, and then we are given f of 1 equals 3. And sorry about the typo here. I would like that to be root log x, not root log t. That's a leftover from an older thing we used to do. I'm just going to do this right here. So I'm giving you f of 5, and I'm giving you f of 1, but then the other piece of information I'm giving you is f prime. So anytime I give you information about f prime and I want to know something about f, what are you going to have to be doing somewhere? You're going to have to be doing an integral. And specifically here, you're going to want to do a definite integral. Anybody want to take a shot at maybe the expression or the equation you could set up? Yeah, go ahead, Matt.
F of 1 plus the definite integral from 1 to 5.
Sorry. F of 1, I missed the last part there.
The definite integral from 1 to 5, f prime of x dx equals f of 5.
Equals f of 5. That's really well set up, isn't it? Basically what he's doing there is he's saying the initial value plus the change equals the final value. You could have thought about it a little bit differently. You could have thought about it with the subtraction like we did in the blue above, and then just added the f of 1 over. And of course, we know that f of 1 is 3, so you could have certainly have just put a 3 right there. That would have been okay. But then once you get to this point, it's definitely Math 9 time. And so you just go 3 plus Math 9. Let's go ahead and run that really quick. 3 plus Math 9 of that, and we should get hopefully a good answer. I think I remember it from the other class. Everybody, yeah, this Matt.
5.56.
3 decimals, please. Yeah, 5.56. 1. Okay, we'll leave it right there. That sounds about right. Please don't forget the 3. I know for me, if I'm using Math 9 with something like this, I will go 3 plus Math 9. I won't go Math 9 and then try to remember to put the 3 in at the end. So I go 3 plus Math 9. That way you're not going to forget it. So consider. Any questions? An important question that I would have for you at this point, have you guys seen how the net change theorem has been woven out through everything we've done? Whether we're talking about a leaky tank or velocity or position or displacement or total distance traveled, in every case it's the net change theorem. The definite integral of a rate gives you the net amount of change. Any questions? Got one more. Okay, so this is it for today. Skip over this one. Please, we'll save that for another day. But do not skip over this one. We're going to do the first one right here. I want to give you guys a couple of minutes to think about this one. This is a writing example. So please use roughly one sentence to answer this. It says, Paul's TVs sells TVs at a rate of R of T.
I thought this TV were selling TVs until I thought about it.
Oh, the TVs are not selling. Paul is. Some guy named Paul. So he's selling these TVs at a rate of R of T TVs per hour. Using correct units, explain the meaning of that expression right there. So this is tying together a couple of things. So, like I said, give you a couple minutes to do this. We might have a brief discussion at the end. Give it a shot. I think. So let me give you an example of what this could be. And if something doesn't make sense, please say something. I would say this is the average rate of change of TVs. Is that better, Matt?
Yes.
In TVs per hour.
But you
Hold on. From T equals 0 hours to T equals 12 hours. Are you going to criticize my punctuation again?
The comma's unnecessary.
Okay.
No, it's not.
Oh, okay.
I just needed one more.
There you go.
There
Have
we
2
go.
instead of 0.
We were having a punctuation discussion over
Why
there.
is it the amount?
So, Paul, thank you for asking.
Aren't you integrating?
Not only are you selling TVs, you're asking great questions. Did you hear his question? It's a really great question. Would you say it one more time, a little bit louder?
Why isn't it an amount? Because you're integrating a rate.
Did you hear that? Say it one more time so everybody could be sure to hear it.
Why is it an amount when you're integrating a rate?
His question is very valid because he's saying, why wouldn't it be some sort of an amount instead of an average rate? So let's talk about that. If I were to just write this, integral from 0 to 12 of R of T dt, if that's what I wrote, if that's it, then here would be the meaning of that. This would be the amount of change, or the net amount of change of TVs. He would be right. But here's what maybe you're not paying attention to, and the thing we want to make sure we do pay attention to is the 1/12. The 1/12 is very significant, and not only that, the 1/12 has units. So if I left it at that, then of course, he's right. But if we consider the fact that the 1/12 is there, and the 1/12 has units, here's what it looks like. The 12 came from 0 and 12, right? And what are the units on the 0 and the 12? Hours. And so this would be the amount of change of TVs over the change in time. I'm trying to color code this to make sense. Do you see it? And so if you've got the amount of change of TVs over the change in time, that's the average rate of the TVs, being sold from this place. Okay? Another way to think about it, did you guys notice? I'm sure you did. You guys noticed like this is actually a formula we worked on the other day, isn't it? Isn't that the formula for the average value of a function? So another way to think about this is whenever you see that formula, that is the average value of whatever is in there. So if the integrand is a rate, that's going to be the average value of a rate. If the integrand is an amount, that's going to be the average value of the amount. If the integrand is an acceleration of some kind, then that would give you the average acceleration. So that formula right there gives you the average value of whatever the integrand is, regardless of whether it's a rate, an amount, an acceleration, or some other thing. But you could also look at it in terms of units like this as well. It should make sense, right? And I hope that it does. So guys, we basically have 4 big problems left, and we have 2 days to cover those 4 big problems. And the timing should work out just right. Okay? So thank you for your good attention. Appreciate your hard work. Have a great day.